This video is going to discuss the maximum power theorem. To start with, I just want to remind you about Thevenin's theorem. Thevenin's theorem says that if we have some complex supply circuit like this, we can simplify that. You break the circuit up, so you break at 2 points within the circuit, call them A and B here, and the supply circuit can be replaced with a voltage supply called E Thevenin, and a resistance in series with that supply called R Thevenin. So maximum power theorem states that the maximum power will be transferred from the supply side over to the load when the load resistance is actually equal to that R Thevenin resistance. So that's what maximum power theorem says, that we want to get the maximum power to the load. Now, as we're going to see, that doesn't mean it's necessarily the maximum power we can get out of the power supply, out of the voltage source, but the maximum power that makes it all the way through over to the load. That's what maximum power is talking about. So we're going to just use this simplified circuit down here using the R Thevenin and E Thevenin. In this example, E Thevenin is 20 volts and R Thevenin is 5 ohms. So what we want to do is we are going to determine the total resistance of the circuit, which of course is R Thevenin plus R load. And that'll give us the total resistance. And then we're going to calculate the total current, which of course using Ohm's law is going to be E Thevenin divided by R total. And then we're going to calculate the powers. So we're going to calculate the power being supplied, which is I total times E Thevenin, right? Power law. And we're also going to calculate the power being lost in the resistance here, or in the supply circuit. All right, so remember that R Thevenin is actually representing all of this that we're doing in the supply circuit. And so we're going to calculate that power loss, which using a modified version of the power law, we get I squared times R Thevenin is going to be the loss that of the power that's being used up in the supply circuit to prepare for the load. All right, but it's not making it to the load, so with that respect we consider it lost power. And then we're going to calculate the power that actually gets to the load and utilized in the load. All right, so to start with, we're just going to do this for five different loads here. So the first load is no load at all, which means that we would have a direct short circuit. So we would just have a short circuit going from points A to B with zero resistance. Okay. So if we have a short circuit here, that would give us 0 ohms. And so R total would be the 5 ohms of R Thevenin plus 0, which of course would just give us 5 ohms. Alright, so if we calculated then the voltage, or the current in the circuit, right, is going to be the 20 volts divided by R total, which is 5 ohms, which of course is going to give us 4 amperes. Okay. So notice that if our load is shorted, right? There's no other resistance other than R Thevenin in the circuit. So therefore, that's going to be a maximum current. So we're actually getting maximum current at this point. The power being supplied, right? The power that this power source has to supply is going to be the E Thevenin times the total current, 4 amps, which is going to be 80 watts. All right, so we're getting 80 watts. But let's take a look here. The power being lost, okay, the power lost is I squared R, which is 80 watts. And the power getting to the load, well, since the load resistance is 0, right, so this is I squared times R load, but our load is 0, so therefore there is nothing getting to the load. Nothing at all. All right, it's all being utilized inside of this supply circuit. So let's take a look at a case where we actually have some resistance now. So let's say that the load resistance is 2 ohms. If that's the case, then our total would be 7 ohms. And so 20 volts divided by 7 ohms would give me 2.86 amperes. So our current has dropped, our total current has dropped, and therefore our supply, our power supplied is also going to drop, right? So I times 20, so this is going to give us 57.1 watts. So our power being supplied by the source has dropped, but there's still a lot of power being used in the R Thevenin. And so if we calculate that, that's going to be 40.8 watts is being lost in R Thevenin. And what's getting to the load turns out to be 16.3 watts. Okay, so what's making it to the load is 16.3 watts. All right, so now let's take the case where our load is equal to 5 ohms. Now remember that R Thevenin was given as 5 ohms. And now I'm going to say let's use a load where these are equal. All right, and if we come back up here and remember here, according to the power theorem, this is when we should get maximum power. So let's take a look and see here. So we get 5 plus 5 gives us a total resistance of 10 ohms, which gives us a total current of 2.00 amperes, which gives us a power supplied of 40 watts. Now, and the power lost, right, is I squared times R Thevenin, which turns out to be 20 watts. So we're using half of that. Half of that 40 watts is being used up in this supply circuit. But 20 watts is also making it over to the load. All right, so as you can see, the power, so far, the power making it to the load has been going up, but the power lost is going down. All right, and of course the power being supplied is also going down. All right, let's look at the next case here where the load resistance is 10, which gives me a total resistance of 15 ohms. And therefore, my current now has dropped even further. It's going to drop down to 1.33 amperes. And the power supplied then becomes 1.33 squared times the 20 volts, which gives us 26.7 watts. So that's 26.7 watts being supplied, and the power being lost is 1.33 squared times our Thevenin. So the power being lost turns out to be 8.89 watts, and the power being supplied, or making it all the way through the supply circuit to the load, turns out to be 17.8 watts. All right, and so we can see now, wait a minute, we were going up, but now we've gone down. Okay, so let's just do one more here. Let's go all the way up to 1,000 ohms for the load. So our load resistance has actually, the load resistance has increased, which means the actual load on the supply has decreased because the current is decreasing, right? So if we see this now, so now we got 1,005 ohms. So there's 1,005 ohms, which gives us a current now. Our current has dropped dramatically, of course, because our load resistance has increased dramatically. So our current has now dropped to 1.199 amperes. And our power supplied then has dropped all the way down to 0.398 watts. And the power being used, and I'm using just keeping everything in units of watts so it's clear to see here. 198 watts are being used, and that leaves 3.96 watts to actually make it to the load. So we can see here that the power to the load is going down as our resistance increases, and the power to the load was increasing here. So as we went from 0 up to 5 ohms, from 0 to 5 ohms, power increased. And from ever since we got over the 5 ohms, so when we went over the 5 ohms and our resistance kept increasing, our power started dropping again. So if we tried to plot this, right, if we plot this versus the resistance, our load, okay, and the power to the load, we end up seeing some plot that kind of looks something like this, where the maximum power occurs at our Thevenin. And so we can see that we basically just verified here the maximum power theorem. So you get the maximum amount of power through the supply circuit over to the load when the load resistance is equal to the Thevenin resistance.